That's funny. Also, I have a real quick like polymer property question.
Great. Yeah, class is almost started, so go for it on the
Oh,
technical
perfect.
stuff.
Okay.
Yeah, go ahead.
So as far as like toughness, I understand like mathematically it's the area under the stress strain curve, but like what does that really mean? That it like if you pull on it, it can withstand stress before it breaks?
Yeah. So the scientific definition of toughness is, you're right, it's the area under the stress strain curve. But what that means, like physically, what is a tough material physically? It means that it's both strong, so it has a high modulus, which is the y-axis on the stress strain curve, and it stretches or it gives, which is the x-axis on the stress strain curve. And so that's basically the explanation of that integral. Is it's high modulus, so it's hard to pull, but it elongates. Like glass is really hard, but it's not tough because you can only strain it like 0.3% and then it shatters.
Gotcha.
But metals sometime will be tough because when you pull on a metal, you actually draw it out a little bit, and the stress strain curve sort of goes in that diagonal before it breaks. But if the material is too soft, you can stretch it and stretch it and stretch it, and it never has a very high modulus, so it just goes a long distance out on elongation. But we really call those elastomers and not tough materials, even though they are, because the area under the stress strain curve is large when they extend 700%. But the units, so there's something called fracture toughness, and it has units of energy. And so it's a description of how much energy you have to put in a material to crack it or to propagate a crack or break it. So there's a couple different scientific measurements of whether it's fracture energy or whether it's fracture toughness, or whether we just say toughness, and the units are in megapascals because elongation is dimensionless, right? And so it's depending on what field you're working in and depending on what materials you're using, different communities will define toughness differently. But the generic idea is it's strong and you can elongate it, because if a material doesn't elongate, that means it can't take shock very well. We go back to glass, right? You drop something that's glass, and it doesn't break because it's weak. It breaks because it can't withstand any deformation. And so if you take something that's really hard, like a piece of steel, right, and you drop it, it doesn't fracture because the strain to break of that material is at least a few percent, or at least 10% or something like that. So it can withstand the deformation or the shock of dropping it. So that's, again, a qualitative description. And you see, you sort of need to look at the units, look at the different measures of toughness, and then how different communities describe toughness. But that elongation is critical, because materials that aren't tough, ceramics, glass, etc., have very low elongation to break. So no matter how hard they are, no matter how high the modulus is, they're never tough because they can only extend just a very little bit before they crack. So we call them brittle.
Gotcha.
Does that work enough? Yeah. Good question. Good materials question. Any other questions? Any questions on the homework? Are people finding papers that they're okay with? Remember, that homework's coming up. It's due on Monday, so you have the weekend to work on it, but you should feel like you're finding a paper, or at least starting to think about what a reasonable paper might be, so you can address the homework. But I'd be happy to chat about anything. Okay, let me figure out how to share again. All right, there we go. And I'm going to back up a couple of slides here in a second, but we left off here last time talking about we have to build a solid part out of material extrusion AM, but we only are able to build a solid part out of the units that are extruded in our material extrusion AM process. And those units are called rods. And so I'm going to go to lecture 4.5, which you should find in the folder. And so I just wanted to remind you all of what material extrusion AM is. Now, I know that most of you have had exposure to additive manufacturing and 3D printing, but there's a couple of you in class that haven't. And so, you know, we're just going to take 5 minutes here. We're going to watch a YouTube video so we're all aligned on what this means. And I just want to talk through the process so no one feels completely lost about what the physical situation is here. So I think I have a YouTube video queued up. Here it is. You might want to adjust your speaker volume because I think this has the standard YouTube music on it. Let me adjust my volume here. Okay, so let's watch this video. It's not very long.
Fused deposition modeling, or FDM, is a layer additive manufacturing process that uses production-grade thermoplastic materials to produce both prototype and end-use parts. This technology is known to accurately produce feature details and has an excellent strength-to-weight ratio. FDM is ideal for concept models, functional prototypes, manufacturing aids, and low-volume end-use parts. The FDM process begins by slicing 3D CAD data into layers. The data is then transferred to a machine, which constructs the part layer by layer upon a build platform. Thin thread-like spools of thermoplastic and support material are used to create each cross-section of the part. Similar to a hot melt glue gun, uncoiled material is slowly extruded through dual heated nozzles. The extrusion nozzles precisely lay down both support and thermoplastic material upon the preceding layers. The extrusion nozzle continues to move in a horizontal XY plane while the build platform moves down, building the part layer by layer. The finished part is removed from the build platform and cleaned of its support material. Raw FDM parts have visible layer lines. However, service providers such as Solid Concepts offer multiple finishing options to create smooth, even surface parts including hand sanding, assembly, and cosmetic paint. Since FDM parts are constructed with production-grade thermoplastics, including ABS, polycarbonate, and Ultem, they are both functional and durable. FDM is utilized in a number of industries, including aerospace, automotive, industrial, commercial, and medical.
All right, can everyone hear me again? Yeah, so that just gives you a basic understanding of, let me bring up the chat too. If you have a question, you can drop it into the chat or you can just unmute yourself. But I wanted to make sure that we're all on the same page with what material extrusion AM is. And we'll do this for SLS, we'll do this for stereolithography, we'll do this for high-speed sintering and binder jetting and others. But, you know, if you haven't seen a 3D printer live, you know, YouTube is a good resource. If the labs ever become public again, we have a lot of these printers in the labs, or you can ask one of your friends for a tour if we can get guests into the labs again. So I just wanted to make sure that everyone's on the same page. And so the idea is that you have to build a three-dimensional solid part showing something like this. but you can only do it with this nozzle tracing each piece of the part and then having layer by layer buildup. And so you need to think about the different layers. So layer 1, 2, 3, 4, etc. So we have layers. And those are separated in time because you build one layer at a time. Then you build the second layer, then the third layer, then the fourth layer. So the whole layer is completed before the machine moves in material extrusion AM. But then you have roads that have to be put next to each other, and this is distributed in time as well. We'll talk about thermal cycling and how the temperature goes up and down in the part as it's made using material extrusion AM. But this is quite a bit different, or it's completely different than what happens in injection molding, or it's a little bit the same as machining, as CNC machining, although that's a subtractive process from a solid block of material, not an additive process. But this idea that it takes time to build the part, you have different layers that are built as a function of time, and then you're trying to build a solid object out of these roads is something that we all want to consider in the next lecture and a half as we talk about this. Are there any questions or any clarifications that people want to make or comments they want to make before we move on and start talking about the nitty-gritty of how this is done? Okay, so this is important thinking about this constitutive unit, because in order to get everything fused together, or in order to build our part out of these roads, we need to think about how polymers weld together and how polymers deform. And so we have, let me get my pen going here. So we have adhesion and deformation. And these are actually very related processes, but they have to do with the rheology and the response of polymers and composite materials to temperature over a certain time. And so what you're going to see over and over, and this will sound like a broken record a little bit, but this is how polymers work, is the temperature is important, and the time over which that temperature exists, or the time over which the thermal gradient exists, is really important. And it has to do with the rheology of the polymer. And so we'll revisit rheology and how polymers respond as a function of temperature and a function of time. Because the only way to get polymers to stick together is to heat them up, or you have to wait a long time, and that has to do with rheology and viscoelasticity. So this is, in general, what this looks like. And so even though ideally we say that, well, the roads are going to be perfect cylinders, in reality, they're squished down a little bit because you have some mechanical pressure when you extrude the road into that gap, and they'll fuse with other roads. And so it's like packing soft cylinders together. If you squish them a little bit, they'll squish together and deform. But you often get these gaps. If you look very closely at an FDM part, you see the lines on the surface of the part, but if you cut the part open, you can also see the gaps between the roads. And these gaps don't have any mechanical properties. You know, it's air. This lowers the density of the polymer as well. And so if you have less material in your part, it's naturally going to be weaker. And then you have all these interfaces where the part can crack. If anyone has ever made a part using material extrusion AM, you know that layer adhesion is important. Sometimes you make a part and it's really easy to break between layer 5 and layer 6, or between layer 10 and layer 11 because that layer is weak. And so this starts to give us some tools to think about how you might accomplish good material extrusion AM and what some of the parameters are. And this is covered in a general way, again, in this paper right here that I brought to your attention last time. This gives us some general ways to think about how we might design what we might call B here, which is the layer height, and A, which this is showing the diameter of the road, I guess B, so 2 times B, layer height equals 2 times B. And A, sorry for the extra arrow, this could be the road. Nope, hold on. Road spacing, which is 2 times A. So how spaced apart are the roads and how spaced apart are the layers? And those are machine settings that you can put into the software. But the result is that you have some delta, which is some overlap in the difference between the extruded road diameter and the layer height. And then you can also have a parameter, I think they call this theta in the paper, I think it's coming up, where you need to make sure the roads are close enough together, or they call it big delta. You need to make sure the roads are close enough together, otherwise you get gaps, so you get road to road gaps. So in this diagram, the layer height looks good because we're getting good layer adhesion. But the road to road distance is bad because we're getting gaps between roads that are sitting on top of one another. So this is really interesting because now you would anticipate that the part is going to be, if we pull in this direction, this is going to be a very weak part, whereas we've got reasonable strength in this direction because we have good layer adhesion. So from this microscopic view, you can tell right away that you're going to have issues in one direction of the part, and perhaps those issues will be mitigated in the other direction. And so we call this difference in properties anisotropy. And this happens in all different kinds of AM, but now we can see where that anisotropy comes from. Not only do we have anisotropic building blocks or these roads that we're using, but we also may have different fusion phenomena in different directions, which also introduces anisotropy. And so this is important to think about. In lots of cases, the machine and the material are all set up, so the parameters are known. You just use the recipe that the company gives you if you're using an off-the-shelf material with an off-the-shelf machine. But in the instance where you're trying to develop a process, or you're trying to test a new material, or you're trying to come up with a really complex part and take advantage of this anisotropic property of 3D printing. This is something that you as a scientist or engineer out in the field is going to have to think about and deal with. And so doing mechanical property testing is a function of direction, doing microscopy. So this is probably an optical micrograph. So optical micrograph. I'm sorry, this doesn't have any scale bar on it, but we can go to the paper and see what the scale bar is. You'll have to do some optical microscopy, figure out where the defects are, but this is how you start to develop a robust process and get to know what's going on with your material as a function of the printing conditions. And there is no one size fits all. So if someone hands you a printer and hands you a reel of polycarbonate, it's really hard to get the first print working or to know exactly what the conditions are. There are some starting points, and we get those starting points from the injection molding literature or from manufacturers' recommendations, but then there's a lot of tweaking that you have to do to get robust parts. And anyone who's done some 3D printing knows that it just takes some experimenting. Any questions on that? I just want to make sure that physically everyone's oriented to what the problems are and some of the considerations. And when we build a part out of powder, or when we build a part out of solid 2D layers, like in stereo or digital light projection stereolithography, you know, we're thinking about some of the same issues, although the constitutive unit is different. But these are sort of some of the classic materials and geometry issues that show up in additive parts. And we'll connect this back to polymers and composites in a sec. Any questions? All right, we'll keep going. So as you start to roll this all together, so you have a negative small delta, which is the layer height, and a negative big delta, which is our road-to-road spacing. You can decrease gap defects, which are shown right here, but you can't get rid of them. It's very, very difficult or nearly impossible based on this geometry in order to get rid of these gap defects. And so there will always be these small pinholes, which doesn't necessarily make the part not gas tight or not watertight. You can make a cup out of material extrusion AM and it holds water, or you can make a mask and it acts like a solid piece of plastic. But there will always be these gaps in there. And so the gaps decrease the bulk density. And that automatically decreases overall strength. And so if you put air into a material, its strength is naturally going to go down, and that's what happens in FDM. So oftentimes if you can get 80 or 90% of the ultimate strength of the material with material extrusion AM, you're doing a good job. And so a rule of thumb is achieving 80 to 90% of material strength is good. So you might have 5% void, and then you have some interfacial issues, which decrease the mechanical properties a little bit further. But there are papers out there that show you only get 50% of the material, of the intrinsic material strength, or 30% of the intrinsic material strength. But if you get the conditions just right, you can really boost that intrinsic strength of the AM part compared to the bulk material. And so you're doing a pretty good job if you can get the conditions optimized just so. All right. Now, it would be really nice if you could have different shaped filaments. And so it turns out that because of the viscoelasticity of polymers, that usually you have a nozzle like this. Whoop, nozzle. And of course you get usual filament. And it turns out because polymers are viscoelastic, even if you have a square nozzle, you'll get a round filament shape because of the surface tension of the polymer. Now you can make that ovalized a little bit, but if you play some games with viscoelasticity of polymers, you can get filaments that start to approach something that's got better space filling if you have this sort of nozzle shape. So this is called the Barris effect, but this is due to surface tension. And visco. And viscoelasticity of polymers. And so that's very interesting because if you could machine this, remember this nozzle shape is a metal component where you have to extrude polymer, then you can start to get filaments that look square. And it might be really interesting if you could pack filaments into this square lattice and get good space filling. But the problem is this is difficult to machine, especially at 500 microns. And if you've ever looked at a nozzle from a 3D printer, after you use it for a few hundred feet of filament, or if you have a composite filament where you have fibers or particles in your material and you're extruding it through that metal nozzle, you get a lot of nozzle wear. And so the nozzle also wears, or it doesn't deform, it erodes as a function of time. And I think I have some pictures of that in a subsequent lecture, whereas if you extrude a composite material for too long, you'll see the nozzle really start to change shape and erode because you're extruding solid chunks of stuff through the nozzle. And so just like sandpaper, your nozzle can erode away. But this is an interesting concept, and we'll see this isn't really commercial. This is just a paper saying what if. This is a really interesting concept where now you could get complete space filling if you could get square roads. So if you go work for a 3D printing company, you can introduce this idea. Okay, I have a question here from Jivtesh. Can't we just 3D print a nozzle like that using, yeah, so that's possible. So the question is, can we print a nozzle like this using laser powder bed fusion of metals? And you can, but remember this diameter is small. So for sort of industrial scale FDM, this could be a 500 micron diameter. Nozzle, and that means that these corners are very small. You need some high resolution there, and you need to get the right curvature because the die has to look like this. For BAM, they might use something like a 1-inch diameter nozzle. And so there you're getting on the size scale that it might be possible to use laser powder bed fusion of metals to get that die made. But you'd have to look into the surface finish. You'd have to look in to see exactly what resolution you can get. And so I think there's some more to do here, especially for larger material extrusion AM. But you know, it's easier to make these parts if they're bigger. So it's possible, but at these small scales, it's very hard to make. And I don't know if anyone doing BAM or some of these larger scale extrusion processes have looked at different nozzles, but that might be something, if people are interested in large scale material extrusion AM, that might be something they want to look into for one of their papers. Good question, Jivtesh. Any other comments, questions people want to make? Okay, so we'll move on. So we've been talking about the shape of roads or the geometry, but we have to fuse filaments together in order to make our solid parts. And so once you extrude a filament, once you have the blocks of material like this, or a part that looks like this, what is the actual molecular fusion process that's happening in order to get this fusion to occur? And there's nice papers by Joe Bartolai and Tim Simpson. They're both at Penn State. And so they've looked at some of this polymer fusion or this polymer filament fusion in detail. This is one cool plot from this paper down here, where this is the temperature cycling versus time. And so you can see just on the order of 35 seconds, you've got a tip that's about at 250 or 260. I think that's 260. Yep, 260. So this is about 260 degrees C extrusion temp. The temperature goes down right away, of course, because the part is cooling, or the filament is cooling as soon as it's extruded. But then you pass over it again. So N+1 is second pass. N+2 is the third pass. And so this head, so this is our heated liquefier, and it's rastering back and forth across the part. That's the geometry. And of course, you can look up this paper as long as I think you're on the VPN. If you can't find a copy of it, let me know. But as you're scanning the scan head back and forth across the part, you're getting temperature spikes. This causes deformation. This can cause warping, but also the repeated temperature cycling is what leads to the fusion of the layers, both layer by layer adhesion or interlayer adhesion, and then road to road adhesion as well. And we'll look at some more of this temperature cycling, because this is just material extrusion AM head that's going back and forth across the part. But you can imagine that this gets really complicated when you're making a three-dimensional part. And there's some really cool temperature profiles in the literature that people have published. We'll get to those. So what's
I have a quick question, sorry.
Yeah, go ahead.
Yeah, so the tool pass N-1 is prior to the material being extruded, correct?
I think that is prior to the data being taken, but I'm not exactly sure. Maybe they warmed up the part with the tool pass, but it doesn't look like they're building a road with the N-1, but I'd have to read the paper in detail. But it doesn't look like a road is being built up there from what they've outlined in the other thermal cameras. And they don't show the tool pass N-1 in the temperature profile. So I think it's just they basically deposited a part, got the camera set up, everything else, and then they just warmed up the part a little bit with the tool pass N-1, and then they started depositing material. But I'm not 100% sure.
Okay, makes sense. Thanks.
Yeah, but the point is that they're getting temperature cycling, and the temperature just doesn't start high and go low. You see this temperature going up and down, and this happens a lot throughout the part. And so why this is important for polymers and composites is because the only way to stick two roads together is to get chains interdiffusing across this interface. So you're not going to be able to see that, but you maybe will see this. So you must have chains, and of course there's polymer chains. Must diffuse across interface of roads to have adhesion. So this is a very weak interface. Because there's no polymer chains spanning that interface. And we'll talk about this coalescence and how surface tension works in this. But the physical picture is, in order to make this weld, as they call it, you need to have chains diffuse. And the only way to have chain diffusion occurs at high temperatures and long times. And so let me clarify that high temperatures is relatively high. For some polymers, that's only 100 degrees Celsius. For other polymers, that's 300 degrees Celsius. And long times is also qualitative. For some polymers, it's a second. For other polymers, it's much longer. It's 10 minutes or more. And we get that time temperature superposition. So let me just write that down. We get that data from rheology. So we fuse thermoplastics by going to higher temperature and going to longer times. And so this plot looks a little bit different from what you've seen before, but if you look at the axes, modulus and frequency, we've looked at modulus versus frequency plots before, and so this is rheology measurement. And of course, we can do this rheology measurement on a rheometer. And if we do the modulus measurement as a function of frequency at different temperatures, we get a stacked plot that looks like this. And we can use time temperature superposition to create this modulus versus frequency plot over a whole range of temperatures. So this is time, temp, superposition. And what they do to construct this plot is they basically shift all these curves so they match up with the other one, and that's called a shift factor. Let's not talk about that. That's the detailed rheology, and if you want to go into detailed rheology measurements, you can take Professor Colby's course where he talks about different shift factors and how you construct this plot over a large range of frequency. But for our purposes, what we need to do is we need to measure the modulus, or the stiffness of the material, over all these different frequencies, and we have built-in temperatures where now you notice that the units of frequency are inverse time. And so now we can either wait a long time and a polymer will have low modulus, because remember, short frequency is a very long time, or small frequency is very long time. So long time at low frequency because of the units. Or we can have short time, and that equals high modulus. So this gets pretty esoteric, but if you go back and remember how silly putty works, and if you haven't encountered silly putty lately, all you need to do is look on YouTube. There are some really awesome silly putty videos, but you know that silly putty, if you leave it on the carpet overnight, it's going to act like a liquid, and it's just going to seep into the carpet or the couch or your upholstery in your car, like I've experienced in my family. But if you take a ball of silly putty and hit it with a hammer, you can get it to break. And so when you hit something with a hammer, you're at extremely high frequency, and silly putty is hard. It's high modulus, and it will be brittle. But if you let it sit there, it turns out that you're at a very low frequency. So this is long times, and then silly putty is very soft, and it flows like a liquid. And this is the physics of how all polymers work. And so you can think of this diagram, this two bouncy balls of silly putty. If you bounce them together quickly, they don't adhere. But if you take two balls of silly putty and push them together very slowly, you can get them to interdiffuse because those chains start to diffuse around. So like I said, this is a little bit esoteric in terms of polymer physics and polymer chain rheology, but this is the only way, the only mechanism that you can use to get chains to stick together and to get roads to stick together. Otherwise, you have to resort to some engineering solution, like putting glue between the layers, and you have a paper on that in your reading if you want to take a look at that, or doing something else at the interface to help that interface fuse. So I know that this will be very new to some of you, but if there are any questions or any clarifications that people want to bring up or comments to make, you can do it now, because this is really how we understand melt processing and road adhesion in these material extrusion AM parts. Any questions? Okay, well, this is something to study, and I think a couple of the papers in your homework are on this, and so make sure you at least take a look at all the papers to get familiar with at least the titles, so you can select the one you want. So the problem with time temperature superposition is that there are limits. We can't heat up polymers to 1,000 degrees C and get them to fuse quickly, and we can't wait 3 hours for our FDM part to fuse, because we'd like to do 3D printing rapidly. And so we'd like to process at low temperature and at fast times, and both those things are working against us in FDM. But fortunately, there are some tricks. And so in order to get adhesion between roads, all we have to do is we have to figure out, how do we fuse all of these things together? And so this is a really nice paper where now they coat, let me go to this diagram first. They coat a neat filament. So a neat filament is just a filament off the reel. They coat it in a carbon nanotube coating. So now this is a nanotube, or let's say carbon nanotube, because the carbon part's important. And so when you take a carbon nanotube coated filament, it turns out that your roads, there are carbon nanotubes at interface of roads. And so it's not the carbon nanotubes that are doing the adhesion. This diagram is great because it's saying weak adhesion before microwave heating and strong adhesion after. These are interdiffusion of polymer chains, which makes part strong. We know that now. And so what the microwave heating does is that the microwave acts on CNTs and causes heating at interface. So if you need to make all these interfaces strong, and if you heat only right here where the CNTs are, you can get this interdiffusion to happen. And that's exactly what they did in this nice paper here. Now, they had to do a lot of things to make that happen, namely coating their filaments in carbon nanotubes, but this is a demonstration of localized heating causes this strengthening of the part at all these interfaces. And so this stack of roads should look familiar to you. This idea that you need to get chain interdiffusion between roads to get high strength should start to become part of your thinking about material extrusion AM. And then it's just a matter of what is the engineering and technology to get us to the physical situation where we have good interdiffusion, and that leads to a strong part. Now, it might not be that we get perfect material properties from that, but you notice in this diagram here, where they're doing this process, they're getting material strengths that are on the order of the bulk strength of the part. So the error bars overlap here, so it's hard to exactly tell what's going on. And you have some nanotubes in there that might add to the strength as well. But this is looking pretty good because the bulk expectation is on the order of 40 kilonewtons per meter for the fracture toughness. 3D printing controls are usually bad. So here you're going to have poor interfaces. And so with their microwave RF process, they're able to really increase the interfacial strength, and they're putting nanotubes in there, which might help increase the fracture toughness further. So this is an interesting paper because they talk about a technology, and then they talk about the fundamentals that that technology addresses in terms of what's happening with the polymer. And so it's a nice example of connecting some solution to the physical situation of chain interdiffusion, which is the connection that we want to make in this class. How do the materials behave? What's going on in a composite or in a polymeric material, and how does that relate to whatever additive process we're talking about? Any questions on that? Okay, and I think I don't have the slides in this presentation, but we will talk a little bit about part design. I know that some of you are interested in making engineering parts, like making parts with specific dimensions, or making parts for aerospace, or making parts that have certain strengths in certain directions. And so I think we'll spend a half a lecture next time on not just looking at fracture strength, or theoretically what parts might look like coming right out of the 3D printer, but we'll spend half a lecture on how you might design and print a part using material extrusion AM. But there are other classes in the AMD sequence that go into this a lot, you know, toolpath, software, everything else. We won't do all of that, but if you're curious about different software packages, or if you're interested in some of that knowledge in terms of the engineering design of additively manufactured parts, I can point you to those resources. We're going to try and keep with our charter of discussions about materials and additive, and especially polymers and composites and additive. But if you're missing something in the additive picture that you want to get, just let me know, give me a heads up, or ask questions on the discussion board on Canvas, because there are lots of knowledgeable additive people in the class, so they'll be able to pipe in, or I'll pipe in as well. Okay, any questions or comments? All right. So another thing that we can do with filament adhesion and also toughening is this really interesting paper by Professor Vogt, who's in the Chemie department at Penn State, and some of his papers are online for your homework if you want to take a look at it. But what they used in this paper is a core shell filament, and they did some really nice CT scanning, which we'll talk about in a second. But this core shell filament, they used polycarbonate, core, and a polycarbonate material is strong, but it's hard to fuse. So polycarbonate is a high viscosity material, it's high melting point, and so it takes a long time to fuse that filament together. Surlyn, on the other hand, is an ionomer. It's like polyethylene with some ionic groups in it. So you can look up what Surlyn is. But the Surlyn shell is easy to fuse. And so they get good road adhesion with this core shell filament, but they get very strong structures because of the polycarbonate core. So they have this nice looking diagram here. And so it turns out if you take a core shell filament and put it through your heated liquefier, you get a core shell road. And the reason you get that is because that there's no shear, or there's no mixing shear in the heated liquefier. There's only extensional shear. So basically you're taking a larger filament, which is on the order of 1.7 or 2.5 millimeters or 3 millimeters, and you're pulling that filament. But if you take a core shell filament that's cylindrical and you just elongate it and keep the cylindrical geometry, you still get a core shell structure after the fact. And so that's really interesting, that you can make a core shell filament from this co-extrusion process using regular extruder, and this is how you make a core shell filament. And then that's preserved when you go through the material extrusion AM process, because you don't have any mixing shear in the heated liquefier. So this is interesting from a number of perspectives, but this is the physical situation, so you can take a look at this paper. So what they observed is, again, now they're looking at the impact resistance, which is energy per length. So that's like fracture toughness that we looked at before. But this is giving us an idea of the toughness of a material or how the material can withstand impact. So here's the Surlyn, low fracture toughness. Here's the PC, a low impact resistance. Let me put impact. Because of course, impact resistance is high rate. And fracture toughness, it turns out, is a low rate measurement in most cases. So if you want to be precise about it, they are slightly different measurements, but they're giving you similar information just as a function of time scale. But you see that the core shell now has higher impact resistance than either of the peer materials. And we might call this a composite effect, just like we saw with adding particles to polymers. And so we see that the mixture of materials has better properties than either of the peer materials. And so this is a clear indication of this composite effect. And so there's really interesting stuff going on if you look at the anisotropy of this part, where you have in some geometries threads of polycarbonate spanning the crack, versus if you're going right through, you don't have any threads of polycarbonate spanning the crack. You have anisotropy in fracture toughness due to road alignment. And so that's interesting because of how this is printed. So it's printed in a regular FDM style printer. You can never get threads of polycarbonate spanning the Z-axis. So when you look at the YZ, because you have layers in the Z direction, oops, you can never get threads of polycarbonate spanning from layer to layer. And so your fracture toughness is always going to be lower in that direction because you're not trying to fracture any of these polycarbonate threads as the crack propagates. So that's just some really interesting things you can do with road adhesion. That's some really interesting things you can do with composite filaments. And so we're going to clean up a couple things in terms of characterization, because I've had a couple questions on that and a couple things on part design. And then we're going to move on to another additive process that doesn't necessarily involve melt rheology, although we're going to keep melting in mind, or at least we're going to keep this time temperature superposition in mind, because we're going to use thermal energy to fuse powder when we get to powder bed fusion. And so when Jivtesh in the chat, if you want to bring up the chat, he used this acronym L/PBF, which stands for laser powder bed fusion. That's usually used in the context of metals. But the physics of laser powder bed fusion of polymers is different than the physics of metals because the melting physics is different. So this idea of viscoelastic polymers and time temperature superposition is something that we're going to have to keep in mind for powder bed fusion of polymers as well. And polymer powders are different than metal powders. And so even though the process might be called powder bed fusion in both of them, there's much different things going on. So we need to keep this melt rheology idea in mind as we move forward and as we talk about the different processes that we're going to talk about throughout this course. Any questions on this? All right, so I have just a couple of slides to finish off this lecture on characterization, because as we start talking about different processes, we're going to start to talk about different characterization techniques. We've talked about them already with Jensen's question on fracture toughness. We talked about CT in the last paper. And so, you know, I want to make sure that at least we have a working knowledge of these different characterization techniques. And hopefully, if you have a favorite characterization technique or something you want to learn about, you'll be able to pick papers for the homework to enhance your knowledge there. But I just want to give you a couple slides on this to make sure that we're all speaking the same language when it comes to characterization, or at least we have a common frame of reference. So we've talked a lot about rheology. And so whether it's viscosity as a function of shear rate, or whether it's viscosity or modulus as a function of frequency, you should have this in your arsenal to talk about it. And sometimes people will want to report viscosities. Sometimes they're going to want to report G prime or G double prime. And so you should know what those things are. So the modulus is a property of a static material. We could think of, you know, the modulus of steel, right? Or the modulus of this polymer. It's the slope, the Young's modulus is the slope of the stress strain curve at low strain. So that's one definition that we should keep in mind. The viscosity is the property of a fluid when it's flowing. And so the viscosity of a solid material is infinity. But as soon as that material starts to flow, the material has a viscosity. And so this gets into the weeds a little bit about these different scientific terms. And so you just need to remember this and be able to use them, at least in terms of discussion. And if you want to take classes on this stuff, again, Professor Colby is happy to tell you all about rheology and polymer physics. So we measure moduli and viscosity and something called a rheometer. And so we have a cone and plate rheometer. We have a plate and plate rheometer. So this is plate, plate. Two plates. Of course, this is cone and plate. This thing is called a Couette cell, named for the person who studied it. And so that's just the geometries that you should know. The cone and plate is interesting because it's got uniform strain or uniform strain rate, because as the gap changes, the radius changes as well, and that's why it's a uniform strain. So anyway, these are some of the terms. And then if you buy a rheometer, you can buy a strain controlled rheometer or a stress controlled rheometer. And so there are differences in these two instruments, and you just need to know which one you have. But the software of the rheometer takes care of a lot of the math, unless you want to do the math by hand. And I'll give you a couple of references in the future slides if you want to study up on how to convert between viscosity and modulus, or if you want to discuss the details of strain-controlled rheometry or stress-controlled rheometry. That's fine, depending on how much of a specialist you want to be. But the rheology data and using the rheology data is what we want to talk about in this course. For instance, we're going to have more chance of road fusion here versus difficult to fuse polymers up here. But what we don't have right now is you must have a modulus of X to get road adhesion, or you must have a viscosity of Y in order to have success in additive manufacturing. It depends a lot on machine parameters, cooling, details of the polymer, molecular weight, all of that stuff. And that's where the sort of expertise in running the machine comes in. So I don't have an equation to give you that will allow you to predict the modulus that you need for success in the process, but this gives you some of the fundamentals for what you should think about when you start to attack whatever additive manufacturing process you're interested in. Okay, so the machine helps you construct the data, and then you can use the data to really understand your additive manufacturing process. And so the typical protocol is that you want to do some rheology measurement, and you're going to measure G prime, which is the storage modulus, and so this is the elastic part of viscoelasticity. G double prime is called the loss modulus, which is the viscous part of viscoelasticity as a function of omega here, which is frequency. And so you make sure that you're within the time constraints, or within the time window that gives you a linear response. You make sure you're in the right temperature, all of that sort of stuff. And you get data that looks like this in the linear viscoelastic elastic regime, and then you get nonlinear effects. And one really interesting thing that happens is that as a function of your strain, it's cool that biological materials show stiffening as you strain them. And so that's interesting, because if you try and pull on skin, skin looks, feels very soft and easy to deform when you just pull it a little bit, but you actually can't break it because of this stiffening effect. So natural materials are designed that way, to yield but not break. And so this is just an interesting aside, and doesn't have a lot to do with 3D printing necessarily, other than this shear thickening or this strengthening of a material can get really difficult if you want to 3D print it. Because of course, if something gets stronger when you try and shear it, that's an issue. So you need to think about what are these different relationships. We'll talk about shear thinning in a second. That actually helps us process polymers. But some of these rheological terms are things that you should be familiar with. The other thing that you should be familiar with is this idea of a Bingham plastic, or a material that can support a yield stress at 0 shear rate. And so what this means is that you can deposit a road and it won't flow. So this material, if I can spell material, won't flow when it's at rest. And so that seems like not a big deal for a cold piece of plastic, right? If I have a cold piece of plastic, it's just going to sit there. Of course, it's not flowing. But you can think about right when the material comes out of the heated liquefier, it's above its glass transition temperature. And so if it doesn't have strong Bingham plastic material, you could have a lot of slumping, you could have a lot of deformation in your part that you don't expect, other than this idea that you have a material that supports a yield stress at zero shear rate. So this is just like toothpaste that you squeeze out and the filament stays there, right? It's not like water, it doesn't flow. This is just like peanut butter, where it holds the shape that you want and doesn't slide off your sandwich or your banana or whatever it is. And so this is sort of what we think about in terms of a thick or a highly viscous fluid, but it's a specific property where it holds its shape. So it's related to viscosity, but it's not viscosity, because we can have highly viscous Newtonian liquids, but those Newtonian liquids, by definition, don't flow at zero yield stress, but as soon as you put yield stress on it, they flow. So Newtonian liquids flow under any stress, like gravity or something like that, whereas Bingham plastics can support a shear stress and not flow. So this allows us to do filament printing, and allows us to make filaments that look like this. Let me circle that in red so you can see it. It allows filaments that look like this that we can extrude and we can build parts out of. And we can build parts out of these sorts of fluids that have a shape and that can be supported. And so we're going to talk about a couple of really interesting papers from Professor Lewis in a second to illustrate some of these concepts. But I wanted to just pause here and ask if there are any questions. Up, and I see one in the chat. Yes, so Bingham plastic behavior, or this slide here, depends on temperature. The slope of these lines is the viscosity. And so viscosity, it depends on temperature, but because the Bingham plastic is due to the chains sliding past one another, or the relaxation time of the material, it's both time and temperature dependent. So this Bingham plastic is time and temperature dependent.
Wait,
So,
Dr. Hickner.
Go ahead. Yeah.
Oh, so does that mean like at a certain temperature, Bingham plastic can behave like a Newtonian liquid?
So it can never behave exactly like a Newtonian liquid, except at some high theoretical temperature. So, I mean, it will get smaller and smaller and smaller, but there will always be some sort of finite relaxation. I suppose when the relaxation is so fast that it's on the molecular scale, I guess you could say that the Bingham plastic becomes Newtonian, but you'd have to have a very fast relaxation time. For all practical purposes, you will change the Bingham plastic behavior of a fluid by temperature and time. And the higher temperature or the longer time you wait, it becomes more Newtonian.
Okay, thank you.
So again, we can turn back to the silly putty example. If you heat silly putty up, it relaxes very quickly. And of course, if you wait a long time, silly putty will behave like a Newtonian fluid. And so Eddie's right that you can get these viscoelastic materials to approach Newtonian behavior, but you get up into temperatures that are not physical or not relevant. And so again, this type of Bingham plastic time temperature superposition, all has to do with viscoelasticity. Of polymers. And viscoelasticity is really important for the adhesion that we care about in our materials. And so that's something that we need to keep in mind. Anytime we're processing polymers, we need to take into account this viscoelastic material. So we're going to look at a couple papers by Professor Lewis because she's got some really nice rheology data in her papers that goes along with some of the direct ink writing that she's going to do. So this is direct ink writing, which you know is a subclass of material extrusion AM. And so you don't need to write this foam under thermal conditions, but some of the concepts that she illustrates is important for our discussion on rheology. So any questions at the end of lecture here? Any other comments? Okay, well, we'll be moving off of material extrusion AM soon onto new things. And so if we're not covering something in material extrusion AM or FDM that you really want to know about, now's the time to bring it to my attention. Otherwise, we're going to move on to new processes and some new ideas in the coming lectures. So thank you very much, and I will talk to you on Tuesday. Bye-bye.
Thank you.
Thank you.
Thanks.